great pleasure and immense gratitude that I stand before you today to kickstart this summer school event on high-dimensional probability and applications. So this event would not have been possible without the generous support and unwavering commitment of our sponsors. First, we would like to extend our appreciation to the Vin Big Data Group and to the Vin Group Innovation Foundation, Vin IF. With their support, we have been able to gather some of the leading experts in the field to share the knowledge and expertise to our eager participants. Furthermore, we would like to express our deepest gratitude to the Vietnam Institute of Mathematics and the International Center of Research and Postgraduate Training in Mathematics for their invaluable contribution to this event. Right. Above all, I would like to thank the lecturers, and the workshop speakers for generously dedicating their time to be present at this event. And I would also like to express my personal thanks to my co-organizer, Hung Pham, for all the effort he has put into organizing this event. So we wish you all a productive and successful event. Thank you. Right, and the first lecture of the morning is by Professor Van Vu from Yale University and from the Vin Big Data Group. He's going to speak about perturbation theory of low-rank matrices. Please.
So thank you very much. This is supposed to be a public talk, so yeah, I will spend a reasonable amount of time on the motivation and history of the problems and the applications in computer science and actually in real life. So so to start, I want to mention a few of mathematics, which is in most people's mind is one of the easiest subject, linear algebra. Right? So basically, it's the study of matrices and linear equations. And even in the first year of college, you already know most of the things that you are supposed to know about linear algebra. That you know how to solve a linear system of equations and so on and so forth. But this is an object actually with immense importance in applications, especially engineering and computer science. If you take a course on deep learning nowadays, which is probably the hottest topic on the market, then the requirement courses could be linear algebra and probability statistics. And so with that in mind, why linear algebra is so important, there are two aspects of it. First of all, let me mention a few parameters that you frequently encounter when you study linear algebra. These are the eigenvalues and the eigenvector. More generally, when you talk about non-Hermitian matrices, then we talk about singular value and singular vector. And a theorem which is of immense importance is the singular value decomposition. That give us a decomposition of a matrix in terms of the singular vector systems from left to right and a diagonal matrix consisting of the singular values. And if you are more familiar with the symmetric case, then you can write this. So these are the vector collecting the eigenvectors. These are matrices collecting the eigenvectors of the matrix, and these are diagonal matrix of the eigenvalues. Right. So these things are important because they carry messages and important information in applications. So if you think about, and that is what you have to, what you want to think about is the matrix as data. You can think about like medical data when you know. A matrix when the columns are the names of individuals, and for the rows you have the medical data like blood pressures and weight and height of a person. So it is a data matrix, and all of this particular thing give you or give people very useful insight about the health issues of the populations. Now that's the first reason. So this have meaning. So if you study statistics, then you could have heard about principal component analysis, which is probably one of the first things that any statistician do. Then it's about computing the singular values and singular vectors. Or if you have a huge data points, set of data points, right? So you can think about this. Every people with our vector here. So each of you have d parameters. So every one corresponds to a d-dimensional vector. So you have you have n times d matrices. So you have n persons, and each of them is the vector. Now you cannot view a vector in 1,000 or 100 dimensions. So usually, if you want to view it, you want to view it in 2 or 3 dimensions. And then what people do is actually you take the first 2 or 3 most important eigenvectors or singular vectors here, and most important actually correspond to the absolute value of the singular values. And for that, you will have a 2-dimensional, say, visualization of the vectors. So here is actually the first eigenvector. Here is the second eigenvector. So if you have this, you can write A as sum of lambda I. The transpose when lambda I are decreasing in absolute value, and you take the first 2. And then you have the projection onto the 2-dimensional space spanned by V1 and V2. And that projection is the picture you see here. That's how people visualize high-dimensional data. Okay, now that the first thing I just said is that linear algebra is not simply about you solving linear equation, but the linear algebraic parameters like singular values and singular vectors, they carry important practical messages, and they are basically the things that people compute it every day in computer science and data science. Now the second thing why it is important and play a critical role is about computational side. One thing about linear algebra is that everything here is relatively easy to compute. So if you think about operators related to linear algebra, then usually they can be computed by just using like matrix, vector, product. And that is something very easy to compute. It makes all the algorithm fast. You can easily, by even standard laptop now, solve a equation of 10,000 variables. You cannot do that if you have system of equations of order 2, like you have a 10,000 quadratic equations, and forget about it, right? We can never solve them. But linear is fine. So that leads to the phenomenon that in applied mathematics, people prefer to use linear algebra even if the original problem is not linear, right? So because it's easy to compute and fast to compute, so many problems are linear algebraic in nature, but even if they are not, then you try to reduce it to a linear algebraic problem, like finite method in solving differential equations. So partial differential equations have nothing to do with linear algebra, but you want to a real numerical solution, then actually you reduce to solving a system of equations, linear equations. Yeah. Yes, so that's why in people, if you study computer science, then again, prerequisite here is linear algebra. That, they don't ask you to study topology or number theory, but this is something is the must. Right. Now I'm going with a little bit more into the computational side. The philosophy of computation in the modern days. So when you talk about computation, you say that, okay, I have an equation and I want to solve it, and you want to solve the solution exactly, right? So you have a problem, you want to, to compute the exact solution. That's what we learn in mathematics. In practice, actually, you never need exact solution, right? First of all, we will not be able to compute it because every parameters in mathematics, like number you use every day, like pi and e, you never use it for exact value, right? The computer cannot represent this number to start with. Second, for practical purposes, you never need an exact solution. Now, if anything you think of, you have to estimate the population of this country. It will never be exact because every day there's some new baby are born to start with, and nobody cares. If you compute it exact to, like order of 100%, that's already great. So what people really care is some approximate solution. And if you do something that up to, with the error term 1% or maybe better 0.1%, that is acceptable in O, for all purposes. Now the second thing is a little bit subtle. It sounds like gamble, but it says that actually in real life, you also accept that you are wrong some of the time. Like if you have to do something, and I am pretty sure that my solution is acceptable with probability 99%, right? I would submit it. The worst thing is that your boss or my boss fire me, right? But it's 1% of the time. That's not so bad. There is a chance that some asteroid destroy the Earth tomorrow too. So if you beat that chance, you're already doing great, right? You don't have to be 100%. So here we talk about, random solution. And which is correct most of the time. Right, so these two philosophies actually underlie the development. Well, I mean, most of the development of computer science in the last maybe 50 years, because, well, if you are old enough, you know that in the 70s there's the theory of NP completeness coming up, right? Complexity theory, and people like David Johnson going around and say that everything you want to compute is NP complete. So this is pretty hopeless, right? But if you take these two aspects into your thinking, then actually most the problem, which is NP complete, NP complete means that, okay, it's very hard, or it will take exponential time to solve it exactly. But what you want to know, what you want to do is to have an approximate solution with high probability, right? You have two more freedom dimensions of freedom to play with, and actually you turn a good percentage of this NP complete problem into a solvable problem. And this kind of development actually is the main development of computer science in the last 50 years or so. So one famous example, I want to cite it correctly, is the very much a sentence that captures these two notions, is the notion of probability, approximately correct learning. It's called the pack learning. It was pushed forward by Les Valiant in the 1980s. Which is the foundation, become the foundation of learning theory, which we know that it's developed into the deep learning and all the artificial intelligence applications nowadays. Yeah, but it's exactly what I just said, that capture both notions. You know, when you learn and you have to say differentiate a cat from a dog, then it's enough that, okay, out of 1,000 cats, you make one mistake. You say that it is an apple, that's also fine. Now, so now you know the philosophy that will underlie also our study here. Let's go back to real data. So as I said, matrix theory or linear algebra in general are interesting because very frequently data in real life is represented as a matrix or sometimes as a vector. So if you want to learn something global about this data, then basically that will reduce or to this computational task of computing the singular value and singular vectors and then projection like that. Now, but data in real life are nasty. There are two properties. Two assumptions that people frequently make. The first is that the data is noisy. Data is noisy simply means that every entry have a chance of having some error term to it. So let's say that you have to design a problem, collect data to design a solution for transportation issue in the city, right? And an entry here, maybe the number of people moving from point A to point B by bus, from 1 o'clock to 3 o'clock in the afternoon, right? And that number you can measure exactly. It will make some mistake, a few people off. So there would be, here maybe a length of a bridge. And, the bridge will change during the days according to the temperature. So it will make a small, even measurement error here. And there's also error you make when you transmit the data or you even record the data. So that is something that you cannot ignore. And that is an assumption that everybody makes. And the next assumption is that they say that the noise is random. So you know that the number of people using buses during that time may be around 1,000. And that number may have some error. Sometimes it is up, sometimes it's down. So it's something like 1,000 plus minus 20. And 20 here means that, some number between 0 and 20 with some distribution. Now, the second thing is that data has structure. Yeah, so people use, the statistician like to think at some point that, okay, data is sort of a random matrix when the entries are like IID, random variables, which is, of course, very fake, right? Because the entries have different meaning in it, and they are, there's no way that they can be IID. You look at the much data in real life, it has some structure. If you look at the picture, right, you will see homogeneous region like this blackboard. You will see the edges of the blackboard. If you look at other data, you will see a different structures. And there are many assumptions here, but one assumption that I saw very frequently is that they assume that the data have low rank. What it means is that if you look at the matrix, let's say m by n, and m and n are huge, they may be of order like 10 to the 5 or 10 to the 6, then usually this matrix has rank of order 100. It's much smaller than the dimensions of the matrix. So the rank is it's some number much smaller than the minimum. So let me illustrate this by a very famous example. That is once a hot competition called the Netflix competition. So if you don't know, then Netflix is a real company, actually, a huge company. What they do is that they release. A long time ago, they used to release CD and DVD, sent by post office to your home, and you pay, and then you can watch the DVD. And nowadays, you just do it online. Right? Nobody is sending DVDs anymore. What's important to them is that the rating of the movies. So the matrix look like this. You have the names here. Here's the customer of Netflix, including you and me. And here are the movies, right? And each person rates certain movies from 1 to 5, I think. Now, the one thing about this is that, of course, not everybody see only a few movies, from the list, right? They could have a list of like 10 of thousands or hundreds of thousands movies. You may see a few hundred, and even from that few hundred, you may rate only 10% of the movies you have seen. So you have a pretty sparse matrix here. Like you have numbers and the rest. Say, let's just fill them out with zero. What is important to them is that they want to guess the other entries, which people have not rated, right? And the reason is very practical. They want to recommend the movie to you. Right? The more movies you watch, the better the business. And you get this recommendation every day. Actually, when you open, your Netflix account and you say that recommended for Van or recommended for XYZ, that you should watch this. And they recommended it on the basis that they guess what you would rate for that movie, right? If you would rate that movie 5, then they would recommend it. If you would rate that movie 2, then they don't recommend it, of course. Now, of course, they don't know, right? They have to guess this number. And they have a system. They had a system to do it, go the side match. About almost 20 years ago, 2007, they create something called the Netflix competition, namely that they call teams to do the guess for them. And the best team would get like $1 million prize. Actually, it's exactly 1 million. It's called the Netflix prize. And what they do is that, okay, so there's a lot of zero here. And what is already rated, namely the real data, they release only one part of that to you. Right? They release only half of the data that they know to you. And now, for instance, what you have is only this. Here, you get a 5 from here, 3 from here, a 3 from here, and a 3. Maybe you get both of these. But they don't give you the whole data that they got. They give you maybe half, maybe some certain percentage of it. And now your task is to complete the whole matrix. And they measure your performance on how well you match the rest of the data, which have not been released, right? So let's say they didn't release this 4. They didn't release this 1. So they are going to look at your score and see that if you match the 4 and the 1 here. And they also compare your rating with the rating of CineMatch, which is a system that they have, which predicts the zero. So this competition took like 3 years. And there are famous people entering it. For instance, Hinton is one of the 3 guys who get the Turing Prize for deep learning. Also had a team which didn't perform very well. So that's not he's not famous for this. But anyway, by the end of the day, there's a team called Belcourt, Pragmatic Chaos, winning the prize. Now this is an ensemble of 3 teams. Belcourt is actually a team from Belcourt. This is the AT&T Bell Labs. And these are 2 different teams that they merged into this team during the competition. So they can beat the sign match prediction by 10%, I think 10.10%. The second team, and they win the $1 million prize. The second team is called the Ensemble. Now they have exactly the same score. And the reason they lost is that they submitted the solution 20 minutes later than the first guy. Right? So this is a 3-year competition. And they submitted 20 minutes late with the exact score. So we try to invite the guys, the winner guy, to Yale to give a talk And it was impossible to invite the winning team because they become so hot, like publicity people. But it's very easy to invite the guy from the second team because nobody knew them. On the other hand, they have exactly the same score. So that's how, unfair life is. 20 minutes. If you have, just your wife go for 20 minutes. Yeah, you lost $1 million. In any case, why linear algebra was important here? Because now the guy from ensemble came to us and he tell the story and so on and so forth. But one of the assumptions he used, right? I mean, he used many tricks, but one of the assumptions he used in this algorithm to recover the data is that the matrix have low rank. And there's the whole theory. Actually, there's the whole theory about why a data matrix have low rank. I wouldn't go into there, but people make argument that to make it legitimate assumption. But here the reason intuitively is quite clear. You have a huge matrix, right? You have hundreds of million users. You have tens of thousands of movies. But what determines a rating depends only on a few parameters of that person. Right? You can look at the person's age, gender, marital status, occupation, salary, education, and so on. And there may be 20 things you can list that already determine more or less the profile of that person with respect to movie. And then you may say that 20 parameters determine that entries, and if that 20 meters sort of determine them in the linear way, then what you say is that the matrix have rank 20. Now, if it's not linear, like most of the cases I say here, then you say that, okay, you approximate it in the Taylor expansion for the first, just take the linear term and say, think of that as approximation of a function of 20 variables. Now, this is not the only trick that the people throw into the competition. There are any other, 20 other purely engineering tricks, which are genius, have to make computer run faster. But mathematically, that was behind this project that make the project is possible at all, right? Because if there's no dependence from the entry, there's no way you can guess anything. You can guess it with from 1 to 5, you can guess with correctness like 20% if it is random. You can only do it if there are dependencies between the entries. And the message here is that the dependence is linear and the parameter is small. That makes the computation feasible. Okay, so now it is about time to do a little bit more math with these two assumptions in mind. So if we collect all the data we have from this Pi blackboard, then mathematically what is the mathematical problem that we have to study? The mathematical problem is this. Right? You have the task, computational task is that you have a big matrix A, and you need to compute, the key parameter of A. Say the first few eigenvectors, eigenvalues. The first few eigenvector may be a low rank approximation of A, right? It is a rank A. Yeah, so A would be this. if you remember this picture, the PCA analysis, or you want to have a two-dimensional visualization of the data, basically you talking about, say, P K of A, which is a projection matrix. Onto the subspace spanned by the most important K eigenvectors, or in general, I would say singular vectors. So these are some of the very first thing that you want to compute. There are many, many other things, but like in the 90% of the problems in practice, you have to compute one of these. By the way, so AK, yeah, so the relation between AK and this is that AK is just a projection of A onto, as a projection pi applied to A. Yeah, so the question is what the math problem is. Is to control the error term in the computation with respect to these two assumptions, 1 and 2. So what I say is that you want to compute things that is useful in real life, then what error term you make under, again, the assumption that also appear in real life. So this is a realistic problem. Yes, so the title of the talk came from here. When we want to control error term of a computational problem, when the data is noisy, namely that every entry is perturbed a little bit, then we talk about perturbation theory. Yeah. Okay, so is it clear, the setting to everybody? So from now on, I will talk about a little bit about the classical perturbation theory. That, again, some knowledge that is taught probably in the first 2 or 3 years in college. And then we will say that under this new assumption, how much improvement can we make there? And then in the second part of the talk, I talk about applications of this new result, right? So I got interested in this. Basically, I create this topic about 15 years ago. But now we have more and more results and connections with other fields of mathematics, and there are tons of applications. It's all very interesting. So a lot of these are still under development, and I would say that this is it is a very probably fruitful period at this point. Yeah, so let me go back to classical perturbation theory. So you have a matrix A, right? And you have to compute some parameter FA. And you can think FA of anything on the right-hand side over here, or any other parameter you can think of that you encounter in linear algebraic course. Now, A is perturbed by some error, right? And yeah, so this is an ideal input. This is a real input. And this is a real output you get. Yeah, and the quite big question is to bound. And for bounding this, you can think of any norm you like, or you can bound it in the relative error term, absolute error term, etc. It will split out into 10 other kind of questions, because I say it because sometimes, yeah, it is much harder question, say, to bound it in the infinity norm than L2 norm, for instance, and it's also more useful. So that, again, there are subclasses of the problem. Okay, so there are typical result of this type. The first one is very inequality. We just say that, let's say you have to compute lambda I of A, the I largest eigenvalue of A, then lambda I of A plus E minus lambda I of A in absolute value is less than the norm of E. And then the norm of E I define as the spectral norm. Which is in the symmetric or Hermitian case, the maximal absolute value of an eigenvalue. In the general case, this is the maximal singular value. And this is sharp, right? Let's say if you consider lambda 1, for instance, which is actually just the norm of A, then this is saying that the norm of A plus E minus the norm of A is less than the norm of E. We just basically say that the spectral norm is indeed a norm, right? It satisfies the triangle inequality. Now, this is in general sharp. For instance, you can take the V equal lambda 1V. So V here is the eigenvector. And assuming that E share the same eigenvector, say this is mu 1V. And A plus E times V is lambda 1 plus mu 1 times V. So this means that you cannot do better than this, right? Lambda plus mu minus lambda equal to mu already. Okay, the second one is slightly more tricky. It's also more interesting. It's called the Davis-Gahan psi theorem. It's about eigenvectors and eigensubspaces. So let's say we want to bound V1 then. Right? So now we have the V1 of A, which is the truth. But the realistic output I have is V1 of A plus E. Right? I want to bound this. So here's V1. And they are, well, the VI, they are unit vector. So all the eigenvectors are unit vectors. Yeah, and so here's the V1 of A plus. And so we want to find the distance between these two unit vectors. And if the distance are not so large, then it's basically the sign between these two vectors. So this B here is roughly the sign of it. So this guy formed the theorem in terms of the size of that. They call the psi theta theorem. But you can think of it as just measuring the distance. Okay, so here's the problem become tricky. So let me show you an example. It's my favorite example, and some of you may have seen that before. I take A to be this matrix. Yeah, let's say A. So it's diagonal matrix with 1 plus epsilon, 1 minus epsilon as a diagonal matrix. So you will see that lambda 1 is 1 plus epsilon, lambda 2 is 1 minus epsilon, V1 is 1, 0, and V2 is 0, 1. Very simple. Now I take A plus E to be this. So basically E is a vector minus epsilon, epsilon, epsilon. D is this matrix. Yeah, so now you see the still, I think lambda 1 is still 1 plus epsilon, lambda 2 is still 1 minus epsilon. Yeah, but the eigenvector here is now rotated 45 degrees. Yeah, well, it's basically the 1, 1 matrix. 1, 1 vector, 1 minus 1 vector. I just normalize them to have norm 1. So this is V1. So I give you a minute to convince yourself it is right. Or maybe I make an error, typo there, but I think it's correct. Yeah, so the stunning thing here is that the eigenvectors are rotated by 45 degrees, namely that theta is 45 degrees, which is quite big, right? And this happens no matter how small epsilon is. So what you learn from here is actually the eigenvector, unlike the eigenvalues, are not continuous in terms of the perturbation. Eigenvalues are continuous because they are solution of the of a polynomial equation, but this one is much more subtle. And the reason for that is that the gap between the eigenvalue is small. So here is only 2 epsilon. And so when the gap is small, there is the danger that the two eigenvectors swap, and and then that causes the discontinuity in the behavior of the eigenvectors. All right, so the theorem is this, that the psi theta, which is approximately just V1 minus V1 of A plus E minus V1 of A is less than a constant. Constant is small, I think either 2 or square root of 2 times the norm of E divided by the gap. Now what the gap means is that if we want to compute VI, then the gap is defined as the max of VI minus VI plus 1 and VI minus 1 minus VI. So, lambda, sorry. Is the gap number I. So distance from the eigenvalues in question to the nearest neighbors. And if you want to say a more general theorem about subspace projection, like now you can, I mean V1 is roughly the same thing as projection on V1. So in the picture that I present here a long time ago, let's say that you want to project the data onto the plane spanned by V1 and V2, right? So you talk about pi 2 right? So you have a plane somewhere and you want to compute the projection on this. Then the projection you can view as an operator or view it as a matrix, right? Orthogonal matrix. Then the theorem here is that again you can have the psi between Vk and Vk tilde. Well, tilde is corresponding. Okay. Or it's the same thing that the operator norm of the difference of that two matrices, because the projection can be represented as a matrix, projection matrix. So it's again less than the norm of E divided by the gap. And the gap here is just have the gap K, which is just lambda K minus K. Because we already take all the eigenvalues from lambda 1 to lambda K. And you care only about one gap. You don't care about the gap from the right, because you already have all these eigenvalues in your projection. You only care about the gap to the right. Right, so this is the Davis-Kahan psi theta theorem. This is again known to be sharp. You know, actually it's already sharp in this case, if you can see. And this is the most frequently used perturbation theorem in I would say statistics and part of computer science. Yeah, so this is a classical thing. So let me stop here. We take a break, and then after that we will do the rest of the lecture is about how to improve these theorems and many other, and how to use them into practical problems, including many that I already mentioned. Okay, so let's take a break now.
in the spectrum, the eigenvector is with respect to which matrix, the A plus E or just A? No, I mean on the spectrum. Yeah. The eigenvector, the eigenvector of the sorry, the eigenvalues.
Well,
my mistake.
Yeah, so let me repeat our plan for this second half of the lecture. So we know a few very basic perturbation bound, and I want to show you that how to get improved bound in the case that we have assumption 1 and 2, namely the matrix in question is low rank, and also the perturbation is random, right? So first I'm going to produce a few conjecture, and then see how far we are in proving this conjecture, and then we go to a few applications. Right, so the first thing is look at the wave inequality here. And you can see that now it is sharp, right? So in the sense that if the eigenvector of V, eigenvector of A, namely V, is also an eigenvector of E, then actually this eigenvector will be the eigenvector of the sum. So the picture is like this. I have V here. Here's A of V, and here's E of V. And then the sum will be A plus E, and V would be this very long vector. Now, if E is random, then actually there's no reason to think that EV have to point into the same direction of AV, right? So if A is random, I would guess that the product E times V would behave like a random vector. And then it have to be more or less orthogonal to V. So if E is random, I would have this picture instead. And let's say this is something of rank equal to spectral norm of E. So actually, if I add these two vectors, I would have a vector like this. So AV plus EV would be this vector. And by Pythagorean theorem, the length of this would be the square root of the sum of the two squares. So it would be something like so this is the lambda 1 square. And so it would be like lambda 1 plus E square over 2 lambda. But less so equal. But assuming that E is somehow smaller than lambda, then it's more or less a correct calculation. Now you would say that, okay, this first of all is observed. It's very stupid because there's no reason that, this sum doesn't make any sense, right? Because AV plus EV is not the norm of A plus V to start with. Right? So this is not the norm. So somehow, even with this, we just have an upper bound on the lower bound of the guy, so which is actually is not very useful. On the other hand, intuitively it gives something. It turns out to be right. It's quite amazing. Yeah, so keep in mind this quantity, E squared over lambda, because we have to subtract lambda 1 anyway. So this arrow term here is not really an arrow term. It's some sort of really stupid guessing of what's going on. But it turned out to be the right quantity to look at. So story here is around maybe 2007. There's a paper of Benarus, Beck, and Pesch. They have something called the threshold phenomenon for addition of random matrices. So what they look at is that they have the GUE, let's say it's a random matrix. So this is a random matrix, a Gaussian random matrix. And they add it to a low rank matrix. And the question is, how can you differ the sum from the purely random one by just looking at the spectral norm, right? And so what they say is that if they discover a threshold phenomenon, that if A is big enough, and big enough, you can exactly quantify it, how big it is. Then the norm of A plus E is bigger than the norm of E. And I think here it's usually by some normalization, it is of order 2 times square root n. Big enough here, I take it as well. In any case, it's the precise theorem. Well, I mean, the BBP thing is discovered for the non-symmetric case. I think the symmetric case, Bayat Nosh and Nada Dikuti, is 2012. And what they prove is this, that A plus E, again, Gaussian model, is equal to lambda plus lambda. If A is Gaussian, E is Gaussian, A is low rank, and of the same order of magnitude, namely the norm of A is comparable to the norm of E. Yes. Yeah, with high probability. Yeah. Yeah, so you can see here, right? So this guy, for most model of random matrices, that, as I said, is order 2 times square root n. So if you see that lambda is square root n here, then you have another square root n here, and you have a match. If lambda equals square root n, then you cannot differentiate E plus A from E by just looking at the spectral norm. Now, if it is slightly bigger, like 1 plus epsilon square root n, then actually this size is going to be bigger than 2 times square root n. And then you can say that you can see the matter. So the threshold happens exactly as well. The witness of this theorem is the assumption that this guy have to be Gaussian, and also this guy, 2 guys have to be comparable. Namely, if I say that, what happens if the norm of A is not order square root n anymore, then they don't know what happens. Um, so this is removed by knowledge. And in maybe around 17 or 19, I don't remember, but more recently. And then for the other part, this assumption, we have a theorem by Son Oruk, myself and Kivang in 2013, say that actually it doesn't matter that E, what order of magnitude of E is, doesn't matter, that E is Gaussian, so it's very general. Random matrix. And very general means that you don't even need the entries to be IID. They quite arbitrary. And what we get is, well, we don't get an equality, but we have a lower upper bound, which is in application the part we care about. So the only difference is the number 4 become number 2. We look the factor 2. Sorry, the 2 is in the even worse place. 2 is here. Yeah, but this applies for almost every model of random matrices, no matter what order of A and E are. Yeah, so let me give you an example, an application of this. Yeah, so you can take the Netflix problem. Okay, Netflix is a little bit hard because I don't define E yet. Yeah, but let's say A is a matrix with positive entries of order 1. Yeah, so sort of Netflix matrix when all the entries are between 1 and 5. The L2 norm of this guy, let's say this N by M matrix, right? So every entry will compute with say N by N. Every entry contribute order 1 to the sum. So this is of order N squared. And because that we have only few eigenvalues, right? R eigenvalues. So this guy is bigger. Again, this guy is also of order N squared. But to be exact, N squared over R, but let me assume that R is a fixed number. So it's lambda 1 would be of order N. And if we take some standard model of random matrices, then the norm of E is order square root N. And bottom line, that the arrow term is of order 1. Yeah, so and also because of symmetry, then you can get a lower bound as well. So actually, the norm of A plus E is exactly the norm of A with the deviation of unit. Now for the Davis-Kahan part, the intuition is the following. Let me say what is the original Davis-Kahan would give in the in the random setting, right? So let me recall the Davis-Kahan. In the simplest case, it's just say that. So this is the 2 V tilde is the V1 of the E. The difference between these two is bounded by a constant times the norm of E, right? Over delta 1. Delta 1 is the gap. And so this is of order square root n. So it's divided by that. Yes, so the main intuition is that which I wrote in my very first paper in 2009, is that if the matrix have low rank, and actually, it's not an n-dimensional problem. It is r-dimensional. And somehow we have to quantify this. So I would want to say that because A have only rank R, so actually all the action happen more or less in that R dimension. Now, of course, technically it's not true because you add random noise everywhere, but somehow we want to bound the fact of that. Now, if this intuition is true, then if we have to guess the conjecture, the guess would be like square root of R over delta 1. Now, but things are trickier than this because this itself is not enough. If you go back to this picture, if the signal of A, namely the spectral norm of A, is small compared to the noise, and actually the noise take over, right? And in the BBP phenomenon, you can even prove that under the threshold, you cannot, not only you cannot see anything from the eigenvalues, you don't see anything from the eigenvector either. The eigenvector look very random. So here, if we ignore the magnitude of A, let's say that this guy is small, then actually this phenomenon cannot be true. We cannot have a very good bound on V1 because all our signal will be random signals. So we have to take into account this quantity as well. It's the noise to signal ratio. Right? Yeah, so I made a conjecture like this, maybe. So now, of course, we can write it in a very much more general way, but let's stay with V1. It would have two terms. Actually, in most setting, I take R to be bounded anyway. So instead of square root R, I just write 1. And to make sure, then we just write big O of 1 here, and big O, I have a tilde in that, namely it has some log term, which you can ignore. But log term always happen in probabilistic consideration. Yeah, so if you are not familiar with the notation, and I don't want to spend time on this. Just think something like this. R is fixed, so we pay 1 over delta 1 for the original Davis-Cahan theorem, namely reduce the square root n to 1. And we have to take into account the noise to signal ratio, which is about the absolute minimum that you have to take into account. So let me just reflect this. I want just to simplify the notation. So lambda is the signal of A. The theorem slow, but so we get the first one in 2009. If I remember well, then maybe something like this, but the next extra arrow term. So the arrow term is we have this extra arrow term. I will explain later. Now, with the two other co-authors, in 2013, we have the general version for the problem of pi. So instead of V1 minus V1 tilde, which is just the projection on the first eigenvector, we have the projection on the span of O eigenvector. So here, so lambda delta here would be delta k, E lambda here would be lambda k. And we still have this extra. Last year, still with the same guy, we have that for the case that E is Gaussian. Now we have what I wanted without the arrow term. Yeah, but it needs to be Gaussian, namely GOE or GUE model. If you don't know this abbreviation, just think about a random matrix when every entry is IID Gaussian. Right, so we get the optimal bound here for this case. Questions, of course, what is general? Because if you study random matrix theory, very special thing you can do for Gaussian, but it's not always easy to do for other models. So there's in the paper, subsequent paper, we think we can do it for IID entries, which are sub-Gaussian. Same result. But the really interesting thing here is a theorem in the future. I think we will release soon by one of my students, Chen, myself. Is that in the general case, when we look at very general random matrices, when the entries are independent but not IID, they can have different variances. And actually, this extra tail arrow term is necessary. They are both there as a bow, and there's also there because it has to be there. It's a little bit strange. It's very hard to explain it in the term of the other two. In the same way as the other two, we have no intuition whatsoever that's why this happened. But it just happened in our calculation, and then we look deep into the analysis. It's actually it's not avoidable. So we can definitely tell that in which case the third arrow term disappears, which is the general theorem, sort of cover both this guy and this guy. And we also tell that in the other cases why you need the other terms. This is more or less the story that we have for this. Right. So now, as I said in the beginning of the talk, that you can generate a lot of problems by looking at different norms. So everything I bow here is in the L2 norms or spectral norm. What about infinity norms? Right? So in this picture, we bow the difference between two vectors in L2 norm, how close they are to each other. You can ask a much harder question than how close they are in the infinity norm, coordinate wise. The L2 norm problem. So if you have to do this, you look at the two eigenvectors, and now you measure the distance in L infinity norm, that you want the coordinates in every single coordinate. Now, if you want to guess, let's say that you know that the L2 norm is this, and actually we know that it is sharp. Let's say this is the L2 norm arrow. So if L2 norm arrow is epsilon given, what can you say here? Manju is an optimistic person. What would you say? So let's say if I am really an optimistic person, I would say this. 1 over square root n times epsilon. Which of course do not happen. Just say that. For the sake that, okay, we can put in some logarithmic term, whatever, into the bound. Now, but that means that all the arrows spread evenly, right? Like in every coordinate. But what is wrong with that intuition that, okay, I have two vectors, they are different, have some difference, and you want the arrow spread evenly in all coordinates. What's wrong with that intuition? If you do real life application, you can see that actually the bigger coordinate should have bigger arrow, right? That happens very frequently. Like if you do something with a big number, the arrow you make there would be much more than something, the same thing you do with a smaller number. So if I am realistic, I would say this. It has to be proportional to this guy. So the second guess would be this. if I have a coordinate which is like 1/2, then maybe the arrow happened there is already, constant fraction of the whole arrow happening to the whole vector, right? And then you cannot avoid this. So it is a conjecture, which we can actually turn into a theorem. Well, sort of a theorem, tilde, in the sense that some approximated the probabilistic version of this. By another student of mine. This is actually more or less true. Yeah, more or less true. I mean, it's not true in exactly this form, but some form that we can compare to this. The difference is not that big. Okay, so that is about the state of the art of this. There's a few more theorems, but it's harder to present, and also the bow become more and more technical. But if you don't have any question now, I will switch into the application. No, this is for very general matter. It's not even IID. Yes. This one? This one. Oh, why it happened? No, this one may dominate both of these. This one may be a big one. Yeah, it is the truth. For certain matter of matrices, actually, namely in that case, is this one actually dominate both of these. There become this the last one. Yeah, a partition of the vertices, and within, let's say the simplest model is between the different classes, we put edges randomly with some probability Q, and within the edges, we put edges randomly with probability P, and assuming that P is larger than Q. So you could say that, okay, we have people with different interests. If you and me share the same interest, then the probability that we connect is bigger than probability that we connect with somebody else from our outside world. And the big problem here is I given you one instance of the random graph. You have to find the cluster. I don't tell you which person belong to which group, right? You have to do the clustering yourself. Is it understood? The easiest thing is when P equal to 1 and Q equal to 0, right? Then the clustering, present itself. You will have P click, right? Everybody connect with everybody, and they do not connect with anybody else. So that's the clustering. But reality that, okay, you will have more H's here, but fewer H's outside. Okay, so there is 1,000 papers on this, and there's all kind of subclasses of this. When we have only 2 clusters, so the bipartite, blended bipartite graph, places where these things are clicked, we have the blended click problem, these things are anti-set, and we have the blended coloring problem, and so on and so forth. Actually, in the paper, we make a very big table just to survey one of these subclass. But anyway, why does it have anything to do with what I said so far? A random matrix give rise to a adjacency matrix. A random graph give rise to the adjacency matrix. So adjacency matrix, it would be just 0, 1. When you connect, you have 1, and when you do not connect, you have 0. So we have a random 0, 1 matrix. Now this matrix have an expectation. So it's A tilde here, and it's the expectation of A is just this core, namely the P and Q matrix. So if I have the partition, then I have to write P within the class, and I write Q otherwise, right? So one of the famous, the very first example of this is, one of the very first example is the hidden click problem. Considered by Alon Riverevich back in the 1990s, I think. What they say is that they have only 2 parts. So V1 is a small one, and V2 is the rest. And you put a click here, so everything is connect to everything P equal to 1. And you put Q everywhere else. So it's basically a click plus a regular, a standard random graph. Let's say just 1/2, a GN half. So basically what you have here is you take GN half and you click out a small, or some small set of substrate, and you have to find that click. Yeah, but it is exactly the setting that fit our theory. Namely, if I name the expectation matrix A, right? The expectation matrix here will have rank K, when K is the number of clusters. So here is only K different columns. Yeah, and then A tilde minus A would be a random matrix E with expectation 0. So an entry here would be 1 minus P and minus P. An entry here for this one would be 1 minus Q or minus P. So in E we see only 2 types of entries. Okay, so let me do it for the hidden click one. Yeah, for the hidden click, right? So your matrix looks like this. You have a big one here. So the alone no problem. Yeah, it's 1/2 here. So this is rank 2, right? Rank 2. Yeah, so the way people solve this kind of problem, let's say in the alone trivial Sudoku, is that they, yeah, so usually it's 2 steps. So step 1, find an approximation. Solution. So namely that they will not find the click, they will find maybe the picture is like this, and what they find is something like this, which is pretty close. And then step 2 is correct. And the reason they have to do this, because they usually do this guy, because they have analysis in the L2 norm. So what they typically do is that, okay, maybe they project onto the subspace spanned by the first or maybe the first 2 eigenvector, because the rank here is 2, and they do the clustering there after the projection. And then they have an L2 approximation, which means that only 1% of the vertices are misclassified. And then they go back and say that if I misclassify only 1%, actually I can correct them to be 100%. But the fact here is that we even have L infinity solution. So actually at the same time I approximate all the coordinates correctly. Then I get them, all of them at the same time. So let me do the computation here. First of all, to make the problem easier, only one step. Thanks to the L infinity approximation. Now, I need a small trick, that namely in the adjacency matrix of this guy, I turn all the 0 to -1. So I will not have a 0, 1 adjacency matrix. I have a 1 - 1 adjacency matrix. It's fair. There's nothing. It's got nothing there. The only difference is that when I make I look at the expectation of that guy. Actually, it's become 1 and 0 matrix. So this is my A. Now this has rank 1, and it has only one eigenvector, which is precisely the indicator of the click. Right? Now, of course, I don't see this guy. What I see is A tilde equal A plus the random matrix. So what I do is that I compute V1 of A tilde, and that approximates every single entry. Well, so this will become like 1.1, 0.9, 1.15. This will become like 0.2 minus 0.12, 0.11, something like that. Let's say that my arrow, L infinity arrow, is maximum like 0.2. And it's easy, right? Just make the threshold of 0.8. Yeah, the expected one have low rank. What? Yes, that's exactly the setting. Like you have the low rank, which is expectation plus the random. And so what I say is that the eigenvector of the realization is very close to the eigenvector of the low rank expectation. The eigenvector of the expectation reviews everything. I have L infinity approximation of that. It also review everything at once. Yeah, and then there are a lot of other things you can do here, hidden bipartite and hidden coloring and so on and so forth with the same principle. Both algorithms are simpler and the proof are simpler than the one you know. Yeah. It's called matrix completion. It's the official name in the literature. And that's exactly what it was about. Like you have a big matrix and we know only like 5% of the entry. So maybe a small part of the entry. The rest, we just write 0. And we have to complete the matrix. Yeah, and as I mentioned, the theoretical aspect of this is that it is doable with the assumption that the matrix have low rank, right? Without no assumption, of course, there's no way to do anything. And there's the famous theorem of Candace and Tao. Addressing this problem. Now, before presenting the theorem, let me specify a potential danger in this kind of problem, namely that you have to forbid certain kind of matrices in this problem because they are very hard to deal with. Assuming that we have, assuming that you have a special case like this, a matrix with a huge entry here and the rest are 0. This is the data we have. Now, if the data is like this, then if we see only 1% of this, then basically you only see 0, right? The matrix have rank 1, small rank. But you can never guess the value of this guy anyway, because the only thing you see is 0. So you have to avoid this type of data to start with. And then they avoid it by assuming something like this. A is, let's look at the spectral decomposition of this, and U and V are the right and the left singular vectors. And we have epsilon, maybe something like alpha is the max of U infinity norm of the singular vectors, or eigenvectors, and assume that this guy is small. Yeah, and to make things simple, let's say that they are of order like 1 over square root n, which is the smallest. It can be a little bit bigger. Yeah, so the theorem here that it is doable. Namely that I desire an algorithm to do this as far as I think it's something like we know. Yeah, so the other question is how small means that how many entries should we observe in order to do this, right? If we observe, the danger is that if you observe a row, which is, we observe only 0 in this row, then there's no way that you can recover that row. So somehow the probability of observation should be big enough to avoid the empty row problem. So it should be at least like log n. As far as the density is better than log n over n, but they have some words. They do log n to the 10 here. And later there is a theorem of this Montanari and author that they managed to reduce it into log n over n, but they have to take another quantity to be small, which is the condition number. So it starts to get technical. So. But I just say that you can have better results by putting more condition, then you can do log n over. And both algorithms are at least hard to describe, so I do not go into this part. It also have several steps like this. You find some approximation, and you correct it to the right solution. So to finish this talk, let me give you a new algorithm that me and my students work on, which achieve this bound, but it's much simpler. And the analysis is also straightforward. So the new algorithm is this. Assume A have rank R, so you can write it as this by singular value decomposition. Sigma R. From 1 to R, right? So this is what we want to know. Yeah, what we see is that a tilde, which have full rank actually, it will look like this. But I decompose it into 2 parts. Plus the rest, which is so these are the largest singular value. So this part is a rank R approximation of A. So I just take this to be B. And now, okay, I wave my hand and say that, okay, first of all, I have to make an assumption here. Namely, I only look at the recommendation system when the entries are the rating of the product. I assume that they are bounded integers. which is fair enough. It's between 1 and 5. Yes, theorem. So there's a two theorem separately by different team actually. Again, me and my student are saying that if you take B to be an approximation of A, and A minus B is less than 0.1. So you approximate the matrix in L infinity norm 0.1. Every entry is correct up to 0.1. So after that, you just have to round them off. So the algorithm is compute B. And the reason we can do this is we approximate this thing very well. We approximate this thing very well in infinity norm. We approximate this thing very well in infinity norm. So the whole sum is well. So we need two theorem because of the log business. Yeah, doing the log n to the 10 is not so bad. So we can do here like log 3. Now reducing to log n over n is sort of work in progress that takes a very long combinatorial lemma. In practice, it doesn't matter. There's no difference. Log to the cube and log, but and well, to do this actually is give birth to some huge constant anyway. But for theoretical threshold, it is look impressive or anything. Yeah, but and so this guy is not written up completely. This guy is written up already. Yeah, yeah. But the bottom line is this: you every entry, and that is the power of this theorem. Okay, so thank you very much. you can look at the total number of entries, right? And it's a pretty good representation for the density.
We were done for the morning sections. The afternoon section resumes at 2 p.m. in a different building, 301. And we have lunch now. Okay, so lunch is in the A5 building, third floor.